Yeah,
There we go. Now it's recording. Okay. Sorry about that.
Thank you. Let me just go back for the recording. And so I'm stating the H-cobordism theorem. We have a compact, simply connected manifold of dimension at least 6. The inclusion of either end, it's a homotopy equivalence. Then, in fact, the H-cobordism theorem says this manifold is trivial. It's diffeomorphic to a product. And this is a powerful tool to understand high-dimensional manifolds. And the first example of that I'll give is the example that Smale gave when he reason for proving this theorem. If you have an N manifold, a homotopy equivalent to the N sphere, then sigma is diffeomorphic to the N sphere if N is greater than or equal to 6. So this classifies high-dimensional manifolds that are simply connected and have the homology of the sphere. If they're simply connected and have the homology of the sphere, then in fact, the collapsing map, which collapses all the manifold except one top cell onto the sphere, is a homotopy equivalence. And therefore, by the H-cobordism theorem, it's going to be I'm not sure what I said, but what's actually true is homeomorphic to the sphere. And the proof goes as follows. You take sigma and remove 2 N balls. Let's call them B, N, plus, and minus. So here's sigma, it's unknown manifold. You take a small ball here, B plus, small ball here, B minus, and remove them. You end up then with a manifold with 2 holes, and the boundary components are N-1 spheres, just the boundaries of these 2 balls, Sn-1 minus and Sn-1 plus. And you have this remaining cobordism, which is the complement of these 2 balls in sigma. The fact that sigma is homotopy equivalent to the N sphere easily implies that W is homotopy equivalent to the N-1 sphere minus, say, cross I. Manifold is going to be simply connected because N is at least 6. You take 2 points out of a manifold at least dimension 6, a simply connected manifold is still simply connected. You calculate the homology of W by excision, for example, and you see that in fact W is homotopy equivalent to Sn-1 cross I relative to its boundaries. So N is at least 6, so by the H-cobordism theorem, W is diffeomorphic to Sn-1 minus cross I, where the other end becomes Sn-1 plus. So we've now understood this manifold in 3 pieces. We have down here B minus, then we have Sn-1 minus cross I, nice product, and then we have B plus. Well, if you take B minus and add to it its boundary cross I, this is still a ball, B hat. It's diffeomorphic to a ball. It's the union of a ball and the boundary cross I. So that implies that our original manifold sigma is a union of 2 balls along their common boundary. And that's a smooth result. Sigma is diffeomorphic to the manifold you get by taking 2 standard balls and gluing them together by a diffeomorphism of their boundary. That does not imply that sigma is diffeomorphic to the sphere, but it does imply that sigma is homeomorphic to the sphere. Because take any diffeomorphism or homeomorphism of the n-1 sphere to itself. So any homeo extends to a homeomorphism phi hat from the n ball to the n ball. Okay, I'll prove that in just a second. It's quite easy. But given that, we have two balls and we've got a diffeomorphism gluing their boundary together. But that diffeomorphism extends to a homeomorphism over, say, B plus. So you can take the identity union phi hat mapping B union B plus into the union over the identity. Well, sorry. Yeah, over the identity B plus. Okay, where this was glued together by phi. This is a homeomorphism. It's only a homeomorphism, not a diffeomorphism, because even if phi is a smooth diffeomorphism, the extension is only in general, can be taken to be a homeomorphism. Okay. And the proof of the extension is to find phi hat of x to be 0 if x is the origin, and to be phi of x over norm x times norm x if x is not the origin. So you just cone the homeomorphism of the boundary, just cone it to the origin. So whatever the homeomorphism here, just do the same homeomorphism on every radius level, every radial sphere, and then extend over the origin. It's clearly a continuous map. It's a bijection. These are compact spaces, so it has to be a homeomorphism. Notice that even if phi is smooth, this operation will not extend phi to a diffeomorphism. You'll get a diffeomorphism except at the origin, where the map will be a cone-like map, which won't be a diffeomorphism. Anyway, that's Smail's first consequence. Any manifold homotopy equivalent to the n sphere for n at least 6 is homeomorphic to the n sphere. So you can ask, for this result, what about in less than 6? Just for this question about spheres for a moment. Well, the same result holds for n equal 5, again using the H-cobordism theorem. And in fact, in dimension 5, you prove the manifold is diffeomorphic to the sphere. I'm not going to give you the entire argument, but I'll tell you the central idea. You have a sigma 5. You prove by homotopy theory that sigma 5 bounds a W6, a compact manifold. W6 is contractible. So that's what I'm not going to prove for you, but it's a general fact. So now you do the same sort of argument. You take a ball out of W6, W6 minus a 6 ball is in a bordism between sigma 5 and S5. And it's an H-cobordism because W was contractible. And so applying the H-cobordism theorem, sigma 5 is diffeomorphic to S5. In fact, W6 minus a ball is diffeomorphic to S5 cross I, and therefore W6 is diffeomorphic to the 6 ball, and its boundary is then diffeomorphic to the 5 sphere. So that's how you can use the H-cobordism theorem to classify 5-dimensional spheres. What about 4 spheres? N equals 4. Well, this is a beautiful and incredibly difficult result due to Mike Friedman. Sigma 4 is homeomorphic to S4. And the smooth question is still open. If you have a smooth manifold homotopy equivalent to the force sphere, it's homeomorphic to the force sphere by Friedman's result. It is unknown whether or not it's diffeomorphic to the force sphere. N equals 3, a very difficult and completely different sort of argument due to Perlman. Friedman was 1982. Perlman was 2003. Sigma 3 is every 3 manifold has a smooth structure, and sigma 3, a homotopy 3 sphere, is diffeomorphic to S3. N equals 0, 1, and 2 are trivial. They've been known since time immemorial. That is to say, from the 19th century. Okay. What about, now let's switch back to studying these, from studying these special manifolds, the spheres, to the general question about the H-cobordism theorem. What is its status? Well, it's, again, trivial for n equals 0, 1, and 2. For n equals 3, it's equivalent to Perlman's result, so it holds. The point being, if you have a simply connected 3-dimensional boardism, then its boundaries are H-cobordism, then its boundaries are 2 spheres. And if you fill them in by 3 balls, you get a homotopy 3 sphere. By Perlman, it's diffeomorphic to the standard 3 sphere. So you take those balls out, and what you have is S2 cross I. N equal 4. The purely topological version is true. Sorry, that's n equals 5, off a dimension. Let me forget that. N equals 4. An H-cobordism has to have ends that are simply connected 3 manifolds, and therefore by Perlman are S3. Friedman's result that I alluded to before implies that W is homeomorphic to S3 cross I. And okay, it's not known, so the smooth version, C infinity version of the H-cobordism theorem is unknown. And that it will be true if and only if every homotopy 4 sphere is diffeomorphic to the standard 4 sphere. Because this cobordism here, you cap off the ends, you get a homotopy 4 sphere, it's going to be standard if and only if this cobordism is the product. So the C infinity version is wide open, just as the smooth version of classifying homotopy 4 spheres is wide open. Okay, so that's n equals 4. N equals 5. H-cobordism is true topologically. This again is the same result by Friedman. And it's false in the C infinity category. That was first proved by Simon Donaldson. Using gauge theory invariance, he found a plethora of examples of homotopy equivalent four manifolds that are in fact H-cobordism that are not diffeomorphic. They're algebraic surfaces. And in fact, one can show that there are algebraic surfaces for which there are infinitely many different algebraic surfaces, all of any pair of which is H-cobordism, and none of them is diffeomorphic. So this fails drastically in dimension H-cobordism, smooth H-cobordism and theorem in dimension 5. All right, so that's the status and low dimensions of the H-cobordism theorem. And let me just say, I'm not going to pursue this any further. I mean, I've talked about applying this tool to study homotopy spheres. In fact, the whole theory in smooth PL and eventually purely topological topology that developed around or using the H-cobordism theorem is called surgery theory. And it led to more or less, I won't be precise, classification of manifolds of higher dimension, of dimension greater than or equal to 5. It's not actually a classification because you give things like the homotopy type of the manifold, its homology has to satisfy, but these are simply connected manifolds. So you have to give the homotopy type, and the homology has to satisfy Poincare duality, of course, if we're going to have a closed oriented manifold. And then you have to put in things like the Pontryagin classes. You have to specify them. There are certain conditions on the Pontryagin classes. And then there are only finitely many manifolds that have that data. And there are many very precise statements, but I don't want to try to go into them. But it was a beautiful classification mechanism, or a way to understand what high-dimensional simply connected manifolds look like. And the basic fundamental ingredient is Morse theory. There's also, you tend to, when doing surgery theory, you tend to switch from the Morse point of view to what's called handle body theory. So as I've already said, when you pass an element, when you pass a single non-degenerate critical point, I told you the difference between the starting manifold, boundary minus, and the upper manifold, ending manifold, boundary plus, is inside boundary minus, you have an SK cross D N minus K. In here, you cut it out, and in here you have a DK plus 1 cross SN minus K minus 1. These manifolds have the same boundary, SK cross SN minus K minus 1. If you take these complements, if you take these tubes around spheres out, the complements are diffeomorphic. And what you've done, and you exchange this product for this one using the identity maps on the boundary. So you take W minus W, you cut out an SK cross D N minus K, and then you glue in a DK plus 1 cross SN minus K minus 1. That's the effect, and that's boundary plus W. That's the effect of passing a single critical point of index K, index K, in a cobordism. And this operation of cutting out the tubular neighborhood of a sphere, which has a product structure, and gluing back in the product in the other order, is called a surgery. So boundary minus of W is obtained from, boundary plus of W is obtained from boundary minus by doing a single surgery on this sphere with trivial normal bundle inside W minus. And then every manifold has a handle body decomposition. It's built up from the empty set or its negative boundary by adding handles. And if you look at the levels, each, as you pass a critical point in regular levels, you will have done these elementary surgeries. You will have done a handle, passing the critical point, adds a handle in the cobordism and does a surgery on the level sets. Okay. The idea of the proof, so the overarching idea is we start with our H-cobordism W, dimension n. We choose a Morse function, which in fact is a self-indexing Morse function. Okay, which we showed last time always exists. By a special argument or by special arguments, we remove critical points of index 0, 1, n minus 1, and n, because these involve the fundamental group, well, especially the ones of degree dimension 1 and n minus 1, and they have to be treated in a slightly different manner. Anyway, we get rid of all of those critical points, and then we cancel in pairs critical points P, Q of index K and K plus 1. And we do this starting with the lowest index critical point. So if we cancel 0, 1, and n minus 1 and n, the lowest index critical point will be a critical point of index 2. We will somehow or another find a critical point of index 3 that we can, after rearranging things slightly, we're able then to cancel the pair consisting of P and Q without changing any of the other critical points or what the function looks like near those critical points. We remove that pair. There's another critical point of index 2. We find another one of index 3. We remove that pair. We keep going. Once we've gotten rid of all the critical points of index 2, we do the same thing for critical points of index 3, canceling them against critical points of index 4. We work all the way up until we reach the last level, which is we cancel n minus 3 points, n minus 3 index points against n minus 2. We get rid of all the n minus critical points of index n minus 3. So we're left only with critical points of index n minus 2. But this thing is an H-cobordism, and therefore it's the homology of the manifold relative its negative boundary is 0, and the Morse homology, the Morse chain complex, will now be concentrated in degree n minus 2, and therefore the homology is equal to the chain complex, but it's trivial. Therefore the chain complex is trivial, and therefore there are no remaining critical points of index n minus 2. So in this method of canceling by pairs, we end up getting a Morse function f, a new one, w into minus 1 n plus 1 with no critical points. And we've already seen what happens. What that means, a gradient-like vector field together with this function produces the product structure. We have the flow lines for the gradient-like vector field that go from the minus end to the plus end. Those give us the lines in the product structure. The function tells us how to parameterize those lines, so we actually get the diffeomorphism. So that's the overarching idea. We're going to cancel all the critical points. Mostly we cancel them in pairs, 2 critical points in neighboring indices. We have to do something a little special to get started. Critical points of index 1 and n minus 1. So let me state the 2 main cancellation theorems that we will use. Okay. So the first cancellation theorem this does not require
Sorry, how do you know you have enough k+1 critical points to cancel all the critical points?
well,
are they ordered in terms of the number of critical points?
So let me answer it this way. It's a generalization of the argument I gave at the end, which is, suppose we have no critical points below k. So we've managed to cancel off the lower ones. So the homology of the chain complex, the Morse homology is trivial because we have an H-cobordism, so the homology of W mod boundary minus W is trivial. So homology of W boundary minus W is 0. And the Morse chain complex is 0 for star less than k, because I have no handles of degree less than k. So this chain complex is 0. Its first non-trivial chain group is CK. And then I have the boundary map from CK plus 1. And the next one down is 0, but the homology is trivial. That means the boundary map from CK plus 1 to CK is surjective. Okay? And therefore the degree of the rank of CK plus 1 is at least as big as the rank of CK. Now, that tells you there are at least as many critical points of index k plus 1 as there are of index k. So just counting sets, we have enough. It's a more delicate argument to find, given the critical points down here, I have to do some arrangement to actually find critical points up here that one by one cancel them. That's part of the work of the argument. But at least this very naive homological calculation or weather characteristic calculation, Betty number calculation, shows you that there are at least as many critical points of index k plus 1 as there are critical points of index k. So I'm not going to run out of critical points of index k plus 1 before I finish. Okay? All right. So the first cancellation theorem. This doesn't use high dimensions. I don't think it uses any dimension restriction. And it uses no homotopy theoretical restrictions either. This is a completely general statement allowing you to cancel certain critical points in pairs. And it goes back to Morse in the, I don't know, 1930s maybe. So let's say we have a compact manifold and a Morse function and a gradient-like vector field. And my situation is the following. I have two regular levels, F inverse A, F inverse B, and I have 2 critical points whose values are between A and B. So P and Q are critical points. And they're the only critical points in F inverse A, B. So this is a cobordism with exactly, if I cut it off at the bottom at A and the top at B, this is a cobordism with exactly 2 critical points. Furthermore, there exists a unique flow line from P to Q, T, let's call it. And this is a transverse intersection, meaning if I take any level in between P and Q, and I look at the ascending sphere from P, let's let P have index K plus 1, K will be, the ascending sphere will be of dimension n minus K minus 1. And let me decorate it here with the level at which we're taking the sphere. So this is the intersection of the ascending manifold from P with this level. This is a regular level, no critical points on that level. So this intersection will be a sphere, and I'll denote it. Its dimension is n minus K minus 1. This is a critical point of index K. Comes from P, it's at level L, and that's its dimension. Likewise, we have the descending sphere from Q. Q will be a critical point of 1 higher index, K plus 1. So this sphere will be of dimension K. It's also at level K. This intersection is a single point. So the statement that there's only one flow line from P to Q is the statement that the intersection of the ascending manifold, ascending sphere at level L with the descending sphere at level L is a single point, because every point of this intersection lies on a flow line that flows in minus infinity to P and plus infinity to Q. So these are this intersection parameterizes the flow lines. I'm telling you there's only one flow line, so this intersection is a single point, and it's to be a transverse intersection. Okay, those are the hypotheses. So the critical point P of index K, a critical point Q of index K plus 1, exactly one flow line, which is a transverse flow line in this sense. If you will, the descending, if you don't want to restrict to this level, the descending manifold from Q and the ascending manifold from P meet transversally. The sum of their dimensions is 1 more than the dimension of W, and they meet transversely in the open part of this flow line. Okay. Another way to say it is to cut off at intermediate level. So those are the hypotheses. And then the conclusion is, let's see, I want to say this. There exists a new Morse function F prime agrees with F off F inverse A, B. So this is just a little piece of W. There's more of W up here and down here, and the function and the vector field exist outside of this region, but I'm concentrating right now on this region AB. So I'm going to construct a new Morse function for W that's equal to F outside of this band. F prime has no critical points on F inverse AB. Chi prime is a gradient-like vector field for F prime, and chi prime equals chi off of this region. Okay, so to summarize, we have this band with 2 critical points which are which have a nice relationship to each other. Their indices differ by one, this unique flow line connecting them, and it's a transverse flow line. Under that hypothesis, I can cancel the pair of critical points P and Q without affecting F near any other critical point. So I don't create new critical points in doing this. In the region where there are critical points, F and F prime are the same, chi and chi prime are the same. All I've done is I've changed F in this region to make it straight, to a gradient-like vector field, so that F has no critical points, and the new gradient-like vector field goes from the bottom to the top. So I remove this pair of critical points. I cancel this pair of critical points without affecting anything else outside of this region where I'm canceling. And as I say, this does not need high dimensions. I guess let's take W to be compact just to be on the safe side. I don't need high dimensions. I don't need simple connectivity. This is a completely general local geometric argument. C infinity argument. Doesn't need any homotopy theory. And that's a method to cancel critical points. And that, in fact, is the method that we will use every time we cancel a pair of critical points. We will somehow have maneuvered our situation until we find exactly this situation. And then I'll invoke this theorem, change the function in that little band, get rid of the two critical points, move on to the next. So this is the basic mechanism by which you cancel critical points. The dimension conditions and the simple connectivity and the H-cobordism condition, simple connectivity come in the second cancellation theorem. So as I say, I'm not proving these theorems now, I'm just stating them for you. This is a stronger cancellation theorem. Actually, what it really is a theorem that says under weaker hypothesis than the hypothesis of the cancellation theorem, but under some hypotheses, you can maneuver things until you get into the situation of the first cancellation theorem, and then you can cancel. So it's stronger cancellation because putting it together with the first cancellation theorem tells you there are other contexts in which you can cancel critical points. And this uses all our dimension and homotopy theory hypotheses. So again, we have compact manifold. I guess I want a self-indexing Morse function. Dimension now has to be at least 6. W, boundary minus W, and boundary plus W are all simply connected. And there are no 0, 1, n minus 1, or n critical points of those indices. Okay? K is the smallest index for which there is a critical point. Okay. P is a critical point of index K. Q is a critical point of index K plus 1. So I have, again, this pair of critical points, as far as the indices are concerned, is just like in the first cancellation theorem. And I have, as before, I have a band, F inverse A, F inverse B. These are regular values. P and Q are my critical points in here. A is less than F of P, is less than F of Q, is less than B. A and B are regular values. So just like before. And now I go to an intermediate level in F inverse of L. The ascending manifold from P at level L, intersecting the descending manifold from Q at level L. This is now a finite set of points, not a single point. And these are, again, transverse intersections. If we orient the descending manifolds from P and Q, then as we talked last lecture, then each xi has a local intersection number, which is, because of transversality, plus or minus 1, let's call it epsilon I, and suppose the summation of the epsilon I is plus or minus 1. Okay? So let me just stop there before I state the conclusion and to try to parse what we have here. So I've had to make some assumptions, the dimension assumption, self-indexing Morse function, none of these extremal critical points, which we'll take care of by other means. And I go to the smallest index where there's a critical point. P is one of smallest index. And I'm assuming that there is a Q which at least algebraically cancels it. So in the first cancellation theorem, the intersection of P and Q was 1 point of transverse intersection. So its intersection number was plus or minus 1. So the algebraic intersection of these two spheres is plus or minus 1. This time, I'm not assuming that there's a single flow line from P to Q. There's some finite collection of them. Each one comes with a sign, which is determined by choosing orientations of the descending manifolds of P and Q. If I reverse those signs somehow, I'll change all the signs of these critical points by the same amount, so I'll change the overall sum by a sign. So this statement is independent, that the local intersections add up to plus or minus 1 is independent of how you choose to orient things. Okay, so this is the algebraic intersection number of these two spheres is 1, plus or minus 1, whereas before the geometric intersection number was 1. There was only 1 point. Then one can perturb the vector field. These were, sorry, I forgot to say, we have a gradient-like vector field. It's always assumed. And these ascending and descending manifolds depend on the gradient-like vector field. So you can perturb the gradient-like vector field in some region. Here's A, here's B, here's F of P. There's some region in here between the value of F at P and the value of F at Q, let's say A prime and B prime. You can perturb this vector field, gradient-like vector field, in some product region intermediate between F of P and F of Q until there is only one flow line. And it is transverse, a transverse flow line. Okay, so we had several flow lines. we're going to monkey with the gradient field here. We're going to change it to some chi prime so that these flow lines disappear in pairs and you end up afterwards with only, here's P, here's Q, only one, here's P, here's Q, only one flow line. So you cancel the flow lines in pairs, a plus flow line against a minus flow line, it turns out, of course, and you end up with a single. You cancel all the flow lines except one of them, and it's still a transverse flow line, and then you're in this situation. So by the first cancellation theorem, we can cancel P and Q. So that's the second cancellation theorem. It's stronger. It only assumes an algebraic intersection number rather than a geometric statement about only one point of intersection. But it's a way to replace the algebraic intersection number by that geometrically nice single intersection. You then invoke the first cancellation theorem to cancel this pair. So that's the stronger second cancellation theorem. Any questions about that? So these are the two basic theorems that we're going to use to cancel these critical points, except for the extremal ones, 0, 1, and -1 and n. All right. How am I doing on the time? All right. So I'm now going to assume these two results. I'll come back to them after I've completed the argument, assuming the results. So we assume these. I might say for the moment, but it'd probably be for the rest of this lecture and most, if not all, of next lecture, and show how the argument proceeds. All right. So we need an algebraic lemma related to the question that was raised earlier about how do we know there are enough critical points at level k+1 to cancel critical points at level k. I gave a count argument to show there's at least enough of them at level k+1, but I need an algebraic argument that lines up the critical points at index k+1, or actually changes the vector field and lines up the critical points k+1, so I can match up to each critical point of index k, a critical point of index k+1 that eventually will be used to cancel it. So that's a beautiful algebraic lemma. So we'll need that. And then we'll need a birth lemma. So strangely enough, in order to cancel the low critical points, namely the critical points of index 1 and n-1, I have to create a pair of critical points and then use one of those two to cancel with the critical point of index 1. So to cancel a critical point of index 1, you introduce you do the reverse of cancellation. You form a birth. You introduce a pair of critical points of index 2 and 3 that could be used to cancel each other, but instead you drag the critical point of index 2 across so that it cancels the critical point of index 1. Then you cancel that pair. In effect, you've traded a critical point of index 1 for a critical point of index 3. You do the same thing on the other side for the negative to get rid of the critical points of index 1. So a birth lemma creating critical points of index 2, 3. So those are the two lemmas. And then I'll state those lemmas in just a second, and if I have enough time, I'll prove them. They're not nearly as hard as these cancellation results. You then use the birth lemma to cancel critical points of index 0 and 1. Actually, you only need the birth lemma for the critical points of index 1. And then you turn the function over and cancel n and n minus 1 using the same argument. Turn it over means replace f by minus f and chi by minus chi. Critical point of index n for f becomes a critical point of index 0 for minus f, and similarly for chi. So you can use the same argument for minus f and minus chi to cancel the 0 and critical points of index 0 and 1 for minus f, minus chi. Those are the critical points of index n and n minus 1 for f. So you get rid of these extremal critical points, and then you use the algebraic lemma to line up critical points of index k and k plus 1, k being the smallest remaining index. For each point of index k, you somehow line up so that there's a nice critical point of index k plus 1, which will cancel it algebraically, and then you use second cancellation. Cancel critical point of index k against the one that's matched with it in degree k plus 1. You continue until there are no critical points left. All right. Questions about that before I state and prove the algebraic lemma, state and prove, I guess I have enough time to do that, the birth lemma. So the algebraic lemma. It's a completely trivial lemma. It's one you all know well. You probably may not have seen it in the formulation I'm going to give, but it's a well-known lemma. This is the one place where simple connectivity is used. When we go to the non-simply connected H-cobordisms, everything that I'm saying works for them except the algebraic lemma. And then you have a K-theory obstruction. This algebraic lemma may not be true for the fundamental group you're studying, and you get an invariant called the Whitehead torsion. And it comes up right here. This is the only place you need simple connectivity, it turns out. All right, so the algebraic lemma is, suppose I have two finite rank lattices, L and L prime, and I have an isomorphism, linear isomorphism between them. These are lattices. And I have ordered bases, E1, EK, basis for L, F1, FK, basis for L prime. These lattices are isomorphic, so they have the same rank, so the bases have the same cardinality. Then there exists a sequence. There exists a sequence of bases for L, the domain, beta 1, beta 2, up to some beta t. The first one is the given basis E1 up to EK, and the last one is the pre-image phi inverse of F1, phi inverse of FK. And in this sequence, each beta I plus 1 ordered basis is obtained from beta I by one of the following three operations. By one, interchanging, these are, I should emphasize, ordered bases, interchanging two elements of the basis. So instead of E1, E2, and so on, you have E2, E1, and so on. So you interchange two, just interchange their labels. Multiplying a basis element by -1, leaving the others the same. So we can switch the basis. It's an ordered basis. We can permute them around arbitrarily. We can also multiply any basis element by -1 if we want. And lastly, we can add to E1 any multiple of ER and leave the others the same. Well, I shouldn't say that. I mean, I shouldn't say it that way. If we have a sequence E1 prime up to EK prime, an elementary operation would be to replace E1 prime by E1 prime plus an arbitrary multiple of some other basis element, ER, R different from 1, and leave the others unchanged. Okay. That's the statement. You have an isomorphism of lattices, or if you want, you have two bases for a given lattice, ordered bases. Then there's a sequence of ordered bases that go from the first to the second, where at each step in the sequence, the movement from an ordered basis to the next is either reordering, multiplying one of the basis elements by -1, or adding a multiple of one basis element to another and leaving the others unchanged. That's the thing. That's the algebraic limit. Completely trivial in this case. So let me prove it. Think of this in terms of matrices. So we have a matrix, K by K matrix, a square matrix of determinant plus -1. That's one basis written as columns in the other basis. And the fact that the determinants plus -1 is that these are both bases for the same lattice. It's an integer matrix, of course. And we want to diagonalize the matrix by a sequence of column operations. Okay, where the column operations are interchange two columns, multiply a column by -1, leave the others unchanged, and add a multiple of one column to another and leave all the others unchanged. So these three operations are exactly these three operations expressed in terms of matrices instead of bases. Okay. So now it's a question about matrices, and it's a completely trivial question. Let's look at the first row of this matrix. Okay. Well, since the matrix has determinant 1, the least common, what do I want to say? The GCD of the first of the entries of the first row is 1. Okay. So in some sense, this is a relatively prime collection of numbers. There's no prime dividing all of them, because if it divided all of them, that prime would divide the determinant. So by the Euclidean algorithm, let's consider the minimum of the absolute value of the alpha 1I. So that's m. Suppose it's greater than 1. Then by adding or subtracting one of the elements from another, I can reduce it. Reduce m by adding or subtracting one of the alpha I and 1I from some alpha 1j, and leaving the other. So leave all the alphas unchanged except alpha j, and you will either add or subtract alpha 1I from alpha 1j. So by the Euclidean algorithm, eventually the minimum in the absolute value of the alpha 1I is 1. If it's not 1, you can reduce it. So by induction, you eventually get to 1. So by switching columns, I can, and multiplying by -1 if necessary, I can suppose alpha 1, 1 is 1. And now I make alpha 1, 2 up to alpha 1n equals 0 by subtracting multiples of alpha 1, 1, by that subtracting multiples of the first column from the second, third, fourth, up to nth column. All right, so now my matrix looks like this. Well, look at this minor. The minor made up of columns 2 to n and rows 2 to n. Well, that's a matrix of determinant 1, one smaller size. So by induction, I can make that matrix by column operations in columns 2 through n. I can make that matrix the identity matrix. And because these entries up here are all zeros, those column operations don't do anything to the first row. Once I arrive there, I do column operations, which subtracts the multiple of the second column from the first so as to make this entry 0, and so on. So then I do column operations backwards to get down to the identity matrix. Okay, that's the algebraic theorem. It's completely trivial because the ring satisfied the Euclidean algorithm. If you have a more complicated ring, like the integral group ring of the fundamental group, then you run into trouble. You can't do this argument in general, where the ring, instead of being the integers, is the integral group ring of the fundamental group. And that's secretly where the fundamental group comes in here. This algebraic lemma is about the integral group ring of the fundamental group. In our case, pi 1 was E, so the integral group ring is just the integers. I have the Euclidean algorithm and everything works fine. When I do non-simply connected manifolds, this turns out, as I'll show you later, to be the ring that you have to try to do this argument over, and so there's an obstruction. Can't always do it. So that's the algebraic theorem. Any questions about that? All right, well, I'll state the birth theorem, but I won't have time to prove it today, so I'll start next time with the proof of the birth theorem. So here's the statement of the birth theorem. Again, I'll state it in for all indices, but I'm only going to use it for 2, 3, turns out. So we have a ball in Rn, the unit ball. And some integer k between 0 and n. That's k is going to be the index of k and k plus 1 are going to be the indices of the critical points that I create. All right. Then there exists a family ft of real valued functions on the ball. T is parameterized by some interval minus epsilon. Epsilon's going to be a small positive number. I'm not going to say too much about that. The following properties. First of all, ft is equal to x1, the first coordinate, near the boundary of the ball, in a uniform neighborhood independent of t around the boundary of the ball. All t in minus epsilon. So whatever these functions are, they're the standard first coordinate function near the boundary of the ball. Secondly, ft has no critical points for t less than 0. Third, ft has 2 critical points, so pt and qt, for t greater than 0. F of pt is less than f of qt, and for any intermediate L, same sort of thing I've been doing before. Here's the intermediate level between pt and qt. Oh, I forgot to say, well, forgot to say the indices. I'll say that in just a minute. There's a unique transverse flow line. And it's transverse, which implies the index of Q is 1 greater than the index of P, but let's just fix things. Index of PT is this integer K, index of QT is K plus 1. Okay, so this is I think of this as a birth theorem. This one parameter family is a family of functions that have no critical points in the ball up until 0. 0 is a degenerate critical point, but once you pass 0, you suddenly have, you birth 2 critical points. They're canceling of indices k and k plus 1, and they're canceling in this very strong geometric sense. And the function near the boundary is always the first coordinate. So you see, we can use this result to create critical points. So let me just show you how you use the birth theorem to create critical points. So suppose we have a Morse function, and here's a region with no critical points, and here's a ball, no critical points. And we have coordinates in this region so that the function is simply x1. We're away from any critical points. So take the ball out and put in one of these ft for positive t. It agrees near the boundary with the first coordinate. So I can glue this function in place of the standard function I had across the ball. And if I take t positive, there'll be these 2 critical points canceling critical points. So by sticking this ball in, I create, in a region where nothing was happening, everything was just a nice product, a pair of critical points of arbitrary index k and k plus 1. It's the birth theorem. Of course, the cancellation is really the opposite. The cancellation is the birth theorem run in reverse. I didn't quite formulate it this way, but what you're doing when you cancel these 2 critical points is you're running this movie backwards. And as t decreases, you're taking these 2 critical points, you're bringing them closer together along this line until you create a degenerate critical point, and afterwards you have no critical point. That's the cancellation lemma, and the birth is the opposite. the cancellation lemma run the other way, forward to create rather than in the other direction to remove. All right, so that ends my time. I'll start there next week. I prove the algebraic lemma. I will prove the birth theorem. I think next week I'll be able to prove the birth theorem and also show you how the argument goes using the algebraic lemma and the birth theorem and the two cancellation theorems. Probably do that in the first lecture next week, and it'll probably take me a day to do each one of the cancellation lemmas. Strangely enough, historically, as I said, the first one was due to Morse. It's old. The second one was Smale's contribution, and it's a little easier to prove, though it involves a beautiful idea. Idea wasn't original with Smale, but he was the first one to realize you could use the idea. It's called the Whitney trick in this context. It goes back to Whitney, who was solving a different problem and used this trick, if you will. And it was Smale who realized this trick could be used to produce a second cancellation theorem and therefore cancel things that algebraically look like they cancel, turn those into Morse canceling things, and then cancel critical points. And that's how he proved the H-cobordism theorem. Okay, that's it for today. Any questions before I leave you? Or before you leave me? I am working on uploading the lectures. I was having trouble with Zoom, but Melissa Zhang has helped me out. And just before I came on, I was starting to upload them. So they should be hopefully uploaded later today. First lecture, nothing on the second lecture, and then today's lecture. All right, if there are no questions, going, once, twice, three times. All right, see you in a week or in 5 days.